We represent chemical compounds with chemical formulas. It's like a shorthand. It's going to tell us what elements are present in the compound and the relative number of atoms or ions. So we use subscripts after the element symbol to indicate how many atoms of that element are present. So some examples here. Water is represented as H2O. H2 means there's 2 hydrogens, and O means there's 1 oxygen. We don't write the 1. We don't write H2O1 because if there weren't any oxygens, we wouldn't put the O. And if there's 2 or more oxygens, we'll put some other number. So we're not going to put the 1. Sodium chloride, NaCl, it's a 1-to-1 ratio of sodium and chlorine. CCl4, this would have 1 carbon and 4 chlorines. Sometimes this can be mistaken for carbon-carbon iodine, but we would never write carbon and carbon right next to each other like that. If there were 2 carbons, it would be C2. I've also chosen the font in my slides, in particular because it actually makes a distinction between the number 1, the lowercase l, and the capital I, right? And so I switched the page. This is a lowercase l. When I'm writing by hand, that's a capital I, that's the number 1, and this is a lowercase l. Because those can get confused, and sometimes it's actually really important. So chemical formulas are going to tell us the relative amounts of elements. There are different kinds of chemical formulas. Empirical formulas, molecular formulas, and structural. The molecular is the most common one, but especially in this chapter, we'll also be talking about empirical formulas. Empirical means from experiment. And so an empirical formula is something you can figure out from a relatively simple experiment by finding out what mass of each element combines. And so you can get the relative numbers of atoms in the compound. An example is hydrogen peroxide. So the molecular formula for hydrogen peroxide is H2O2. This is a molecular compound, and each molecule has 2 hydrogens and 2 oxygens. But if you did an experiment and found out the mass of hydrogen and mass of oxygen and figured that out, you would come up with HO, which is the simplest ratio, right? This is a ratio of 2 to 2, and this represents 1 to 1. So the empirical formula is always the lowest whole number ratio of atoms. The molecular formula gives you the actual number. So the molecular formula tells you exactly what's in a molecule. For C4H8, it's got 4 carbons and 8 hydrogens. From this, we should be able to write the empirical formula that has a ratio of 4 to 8. And how can we reduce that? Well, both of those numbers are divisible by 4. And so we end up with the lowest ratio of 1 to 2, and so that's the empirical formula for that compound. In B2H6, this is the molecular formula. The empirical formula would be the lowest ratio, which would be BH3. Carbon tetrachloride, CCl4, that's a 1 to 4 ratio. It cannot be reduced anymore. The molecular formula and the empirical formula are exactly the same. We'll talk more about the relationship between empirical and molecular formulas later on. A structural formula is going to tell us about the structure. It's going to tell us, well, how are those atoms connected and what kind of bonds are connecting them? So it uses lines to represent covalent bonds. We use a single line for a single bond, a double line for a double bond, and a triple line for a triple bond. Which formula we use depends on how much we know about the compound and also how much information we want to communicate. The structural formula is going to have the most information. It's also the most difficult to type into a computer, because you pretty much need a graphing program to draw it all out, and that gets really tedious. So we don't use structural formulas unless we really need them. An empirical formula communicates the least amount, and so that's also not a popular one, because the molecular formula gives us more information and is just as easy to write in a computer. So this is something you should be able to do. This is, possible type for an exam question. Write the empirical formula for the compounds represented by each molecular formula. So we're looking for, can we reduce the ratio? So this first one, what's the ratio of carbon to hydrogen? Is 5 to 12. Can that be simplified? No. So the empirical formula is the same. It's just going to be C5H12. How about Hg2Cl2? Yeah, we can reduce that and have it be 1 to 1. And how about this guy, C2H4O2? Yeah, we can divide all of those by 2 and end up with CH2O. That's the simplest ratio of the elements. But this tells us exactly how many carbon atoms are in a molecule. We can also represent compounds using molecular models. The ball and stick model is common. And if you buy a model kit for chemistry, it's most likely a ball and stick model. So here the atoms are represented by little balls and they're connected by little sticks. This is a common color coding scheme. You do not need to memorize that, but that helps me to recognize that in this little molecule I'm holding up, there's 2 black carbon atoms and 2 white hydrogen atoms and 2 green chlorine atoms. And so that makes it easier to look at it and figure out what it is, instead of having to write letters or something on the different balls. A space-filling molecular model is also used sometimes, and that's going to look like this. The space-filling model is going to more closely reflect the actual shape of a molecule. The ball and stick model gives us some idea about the shape, but the atoms are not really that far separated from each other in an actual atom. They're more like this, where they almost appear to be overlapping with each other, because they actually do that. So they're all kind of squished together. So that's called a space-filling model, because it fills in the spaces between the balls and the sticks. Ball and stick model, structural formula, just showing how they're connected. So, there's the red. That's not red, I know that. It's black. There's a carbon, and we've got 4 hydrogens. This is showing us the geometry of it. This is just showing us in 2 dimensions how it's connected. It's not flat. It actually looks like this. And then the most concise way to express that is with the molecular formula CH4. But these all represent the same molecule. This is a table that just gives you all these different ways of representing 4 different compounds. Let's just talk about glucose. So that's the sugar in your blood. Its empirical formula, CH2O. Molecular formula, each molecule has 6 carbons, 12 hydrogens, and 6 oxygens. But there are a number of other sugars that have that exact same molecular formula. They differ in exactly how those different atoms are connected to each other. So the structural formula will help us to identify that this is glucose and not another one of the hexoses. This would be the space-filling model, which helps us to see more of the shape of this. And this is the space-filling model. So we'll see space-filling models a lot of times in the illustrations in the textbook, and they're really useful, but especially when they're just on a two-dimensional surface, you can't see some of these atoms that are in the back very well. So you would have a hard time writing a molecular formula from that space-filling model because you can't tell what's on the back of it. This ball and stick model has a lot more empty space, and so even ones like this that are behind, you can still see them, and so you could count them.